Hello, everyone. Today we are starting a new unit called circuits. And I have in front of me my slides, my PowerPoint slides, and my notes one. So I'm going to kind of walk you through both of those. So I'm going to start with my slides here. The topic is circuits. And I just want you to know before we get too far into the unit that there are really two categories of circuits. There are what are called direct current circuits, which are DC circuits, and then there's alternating current circuits, which are AC circuits. And direct current circuits, like the electrons keep going around and around and around in a circle, and alternating, which is the kind of electricity that's in your house, the electrons go around and then they alternate and they go backwards and then they go forward and they go backwards. And so this is a lot more complex. So we are not doing AC current. And AC current, again, is what's in your house, and it's probably more what you're used to. We are going to do simple circuits, which are DC circuits. So in terms of our electric circuits, we are talking about direct current circuits. All right, so we are going to start with box number one, and I'll come back to the spots to help you fill them in. But we're going to start with the concept of a battery. So a battery is a device used to convert chemical energy into electrical energy. So if we were at school, we could make a battery by taking two electrodes made of different metals. So like just two pieces of metal pole. So this is an example of a carbon pole and a zinc pole. And then we'd have to place it in an electrolyte. And an electrolyte is just a conducting solution, and acid is a conducting solution. And as soon as I put the two different metals in a conducting solution, then a chemical reaction takes place. And those of you in AP chemistry, it's an oxidation reduction reaction. And what happens is one of the poles ends up being negative, and the other pole ends up being, I wrote that backwards. One of the poles ends up being negative and one ends up being positive, meaning that electrons from one pole went to the other pole, making this one have excess negative charges, and that would leave this pole with a positive charge. But you can make electrons or make batteries lots of different ways. So here's just a picture of, it's called the Baghdad battery. And obviously it was found in Baghdad many, many, many years ago in the BCs. And this just shows that even back in the BCs, they had hollowed out rocks and they were able to construct something that the thought is that this was an ancient battery, that they probably filled this with some sort of conducting solution and had different metals in here and made batteries a long, long, long time ago. You could also make a battery at your house by using like a pill bottle and a piece of copper and a nail. Again, two different metals. You need a conducting solution. Vinegar is technically acetic acid. It's a very weak acid. You could use vinegar. Honestly, you could use a can of Coke. Coke is a weak acid, and copper, a nail, and in Coke, you have yourself a battery. You can also make a battery by the juice in a lemon. So that is a conducting solution. It's kind of acidic. And so this is a picture of a lemon. And there's a penny in one side. There's your copper. There's the nail in the other. There's your two electrodes. And so what I like is that batteries are very complex. And when we go buy them, they're all kind of hidden inside. But we can actually make simple batteries ourselves. And you can see that this lemon battery is giving us 0.869 or 0.9 volts. So that's a pretty decent voltage for a simple lemon. Okay, so let's make sure that we have all these filled out here. So a battery converts chemical energy into electrical energy. It's going to be the energy source in our circuit. And the variable for a battery is going to be V, and V stands for the voltage. Like we need to know the voltage of the battery. And I put over here that voltage is sometimes called potential difference. And why it's called potential difference is because there's a difference in voltage, which is another word for potential. There's a difference on each side of the poles, where one being negative and one being positive. So just note that voltage and potential difference are both the variable V. This part I find is sometimes kind of confusing. The unit is also a V, and it's in casual language called volts. Like my battery is a 12-volt battery, but it's really named after scientist Mr. Volta. So I kind of wish these were voltas instead of volts, but voltage is the variable and volts is the unit. You're going to see in this lesson, as we start this new topic, it's going to have a whole bunch of new vocabulary. And that's really what we're trying to sort out today, the new vocabulary, the new variables, and the new units. When we start drawing circuits and we want to put a battery in a circuit, this is the symbol that we use. We use a little line and then a longer line. And you need to know that the longer line is the positive side of the battery and the shorter line is the negative side. And I remember that by the shorter side, I'll say looks like a negative sign. And so I can see that. So in the next picture here, it shows a battery, but it shows like a short line, then a long line, then a short line, then a long line. So to me, that would be like, I'll call it a 2-lemon battery. So somebody made a battery that instead of having one lemon, they have a second lemon in there. And so we have like two batteries, two mini batteries kind of stacked or put together. So that would just obviously increase my voltage. So you'll see that sometime, but we're just going to treat it like one battery. All right, the next thing then is when we look at the circuits. So a circuit is any continuous conducting path. And so when you look at the battery in real life, and we have a couple light bulbs over here, we have a switch. If you can draw a circle like this, then you know that you have a circuit. Over here, I have a circuit. It consists of 1, 2, 3, 4 lemons and a light bulb. And if I follow it along with the wires, it goes here, and then it goes into the lemon, then it goes here, and then it goes into the lemon, it goes like this, and it goes like this, and it goes. So it's kind of a loopy circle, but the point is I was able to draw it without picking my pen up off the paper. That's a continuous circuit, and you know that circuit's going to work. But when we actually draw circuits, we draw them, I'll say, I won't use the word free body diagram because that's a measure of forces on something, but just like free body diagrams, there's like kind of like rules that you conform to. And so one of the rules that we conform to in terms of drawing circuit diagrams is that they're generally boxy. And so I could say that, okay, so I have a battery and then it comes over to light bulb 1, light bulb 2, and I got a switch. So we turn this whole thing kind of boxy. And over the next couple of lessons, we're going to actually be learning to draw circuits as well. Okay, one more time, voltage, and the unit is volts. And you can see that the long line is the positive and the short line is the negative side. Okay, the next topic then is current. And if I go to my battery here, if this is the positive side of the battery, we know that there's a whole bunch of electrons lining up on the negative side of the battery, leaving this side of the battery positive. So these electrons are going to want to repel each other. And that's what gives the battery its source of power, is that these electrons now want to repel. The separation was created by the chemical reaction, but now they want to repel and they want to start traveling around. They're going to repel from the battery and they're going to enter the wire and they're going to start traveling around the circuit like this. So when it says current is rate of electron flow, I want you to picture the electrons to be like little ants, that they're going to be marching through the wire. And how fast the ants march, how fast the electrons march around the circuit is current. And the variable for current is the capital letter I. And the equation is how fast the charges march per time. So electrons are charges. So it's like how fast these Qs are marching per unit of time. And since electrons are charges, they're measured in coulombs per second. So the unit for current could be called coulombs per second, but we have renamed a coulomb per second after Mr. Ampere because Mr. Ampere came up with this. And so the unit of current is amperes. But sometimes, in everyday language, we get a little lazy and we sometimes call it amps. So it's okay to call it amps, but if you want it to have a variable, it's going to be capital A. And so all of that information can be put here in box number 3. All right, I don't know if you've noticed it though. When I was talking about the electrons and I said that they go this way, the arrows in the circuit are pointing the other way. So we're now talking about box number 4 on your notes here. And this is called the direction of current flow. So I'll explain it and then we can kind of come back here. So back in the day, when people were coming up with the rules of how to draw circuits, the electron technically had not been discovered yet. So they knew that there were marching charges, but they thought they were all positive charges because we didn't know that there were negative charges. And so it was decided back in the day that all of these positive charges on the big side of the battery would repel, and therefore the current would flow this way. And so this is called conventional current. And we use the word conventional current. The word conventional means it's conventional. We've always done it that way. And so we still today pretend that the charge is coming out of the positive side of the battery. Because once we discovered electrons and said, oh my gosh, we had that wrong, they really come out, they really go the other way. So the way they really go is called actual current flow. But by convention, because we always thought they went this way, this is conventional current flow. Conventional current flow. A decision was made that we were not going to change what we've already been doing. So when we have a battery, so here's my positive side, here's my negative side, we are always going to pretend that the electrons are leaving the positive side of the battery because that's the way we do things. I kind of wish that people had cleaned this up a long time ago in the 1700s, but we didn't. So one more time, we are going to pretend the electrons come out of the positive side of the battery, and we show the direction of current flow by drawing an arrow. So I usually draw the arrow right on the wire. Some people draw the arrow next to it like that. All right, the next topic is box 5 on your notes, and it's talking about something called resistance. So in a circuit, as these electrons are trying to march around, they encounter friction. And friction in a circuit is called resistance. And resistance is something that makes it harder for electrons to flow. You might picture it like if you were walking to school and you encounter friction could be like a mud puddle. Friction could be like a snowbank. Friction could be like a mountain that you have to climb over. And so it's the things that the marching electrons or the marching ants encounter that slows them down. So the variable is R, standing for resistance. The unit is named after Mr. Ohm. Mr. Ohm. So we measure resistance in ohms. And we would like to have a variable for ohm. And so you might think O, but they didn't use O because O's can look like zeros. They instead went to the Greek letter O, which is called omega. And omega, capital Omega, happens to look like a horseshoe. So the variable for resistance are ohms, or sometimes we call them horseshoes, but it's really omega. We'll write the word omega down here. All right, well, inside a circuit, we can encounter friction or resistance in a variety of ways. Sometimes we purposely put something in a circuit that's called a resistor, and the wire itself, the electrons trying to walk through the wire, that's also a type of friction, and it has a different name. It's called resistivity, but there's other things that are all part of this general concept of resistance. So we're going to talk about these other ideas also. I guess the last thing is the symbol for resistor in a circuit. So here's my wire. And if I wanted to add a resistor to my circuit or to show the friction, we draw that by doing a squiggle like this. Kind of looks like a 3 pointy triangles. You'll see those in our circuits. Okay, we are now on box number 6 on your notes. So this would be if I went to Radio Shack and I had a circuit and I needed to slow down the electrons. Like I want to purposely add some friction to my circuit. And so those are called resistors. And at school, I have a bunch of little resistors I could have shown you, but they are about the size of, oh gosh, maybe like a pencil, like the eraser on your pencil. Okay, but they're tiny, tiny. And this would be like if I opened up my computer and I looked at the circuit board, you would see these little tiny things here. These are the resistors that we're talking about. And all these little colored bands that are on them, there's a little color chart. And that if I knew how to read the color chart, then we would know the value of the resistance of these particular resistors. So this is a picture, a boxy picture, a circuit diagram to show us that we have a switch over here. We have a battery, and these would be my resistors. But when we draw our circuits, we would draw the resistors as a squiggle, 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 squiggle. And again, a more real life picture there. This would be a light bulb. This would be a slow down resistor. But you know what? Even light bulbs, when I put appliances in circuits, they're resistors also. So this looks more like a real life thing. But if I wanted to draw it boxy, I would say that while I have a battery, there's the positive side, so plus side. I have a resistor that I'm putting in that I bought at Radio Shack to slow it down. And I have a light bulb, that's a resistor. And then I would draw that over there. So you can see that this is like a double lemon battery with 1, 2, 3 things in it that are slowing down the flow of electrons. All right, number 7 in your notes here says that there's even resistance inside a battery. Like when we had that chemical reaction happening and the electrons had to get to the other electrode, they had to like swim through the conducting solution and they encountered resistance. And that is called internal resistance, kind of like it's internal, it's inside the battery. But in all honesty, you and I are not going to do internal resistance this year. So we're just going to skip that one. All right, next we're going to move on to box number 8. And box number 8 is the resistivity in a wire. So as the electrons are trying to march around the circuit, so they could encounter a real resistor like this or a light bulb, which is a resistor, but even marching through the wire itself, there's resistance in the wire. And usually when we draw a circuit, the resistance in the wire is generally pretty small. So we kind of like ignore it. But if you ever need to calculate the resistance that's inside a wire, it has its own name. It's called resistivity. The resistivity in a wire. And the resistivity has its own equation. So I'm going to call this resistance in a wire. And back when I was in college, this is how I memorized this equation. PLA. P-L, PLA. And I just somehow remembered that the A was underneath. PLA. All right, so how do you calculate the resistance in a wire? First of all, this variable here is the Greek letter R, stands for rho. It's the same symbol we used for momentum. It's the same symbol we used for density of a fluid. Now it stands for the resistivity of a substance. So the question is, what is my wire made out of? My wire could be made out of silver or copper or gold or anything else that's not in this chart. And so what is the resistivity value of these things? So you can see that they all have a -8 power, but silver is 1.59 to the -8. Nichrome is 100 times 10 to the -8. Resistivity slows down the flow of electrons. So the bigger the p-value, the more it's going to slow down the flow of electrons. So like I don't want to make my circuit out of nichrome wire because it's really going to slow down the electrons trying to get through my circuit. What do I want to make my circuits out of? I want to build my circuits out of silver wire. Well, silver is kind of expensive. So what's the next best thing on the list? Copper. That's why many circuits are built out of copper. That's why using a copper wire in a lemon works. That's why using a copper penny, a copper coated penny in a lemon also works very well. So copper is a very common material for a surface or for a wire. All right, L is the length of the wire. So let me draw a wire like this. So L is the length of the wire, how long it is. And then A is the cross-sectional area. So like if I kind of cut the wire and I saw this little circle here, so that's the radius. And so obviously the cross-sectional area is going to be area of a circle, pi r squared. All right, so it says sketch a wire with a low resistivity. So I want to draw a picture of what a wire would look like that has a low resistance value and then a high resistance value. All right, so here's my low resistance value. First of all, I want low, so we're going to pretend it's a silver or copper wire. If I have a big L, that would be a lot of resistance. So I don't want a big L. So I want a short wire. Where a long wire, would have a high resistance value. What about the cross-sectional area? Well, if the A becomes big, as this gets bigger and bigger in the denominator, that would make the resistance value smaller. So I want a big area if I want a low resistivity. And that's what I drew here. My cross-sectional area is big and it's fat. That's low resistance. If I have a skinny wire, then I'm going to have a high resistivity. So this is a big R value, and then this would be like a little R value. You can also think of it if you go back to the concept of the marching electrons or the marching ants. So picture you're one of the marching ants, and the wire that you're marching through, the circuit that you're marching through, looks like a pipe. So isn't it going to be easier to march through a short, fat pipe than it is going to be to march through a long, skinny pipe? And if you just look at it from common sense, you can tell which values would be high resistivity values and which would be low. Just think of them as pipes. All right, so if you ever have to calculate the resistance in a wire, this is the equation that we use. All right, we're moving on now to number 9. All right, it says many appliances function as resistors. Basically, if you plug it in, it is acting as a resistor, because when you plug something in, you are stealing some of the electron flow. You're making the electrons now go through your appliance instead of just bypassing it. So therefore, it takes energy or voltage to push the electrons, the current, through a resistor or an appliance. It says, as a result, appliances consume power and generate heat. So here come my electrons. We'll have them marching through the wire here. So they're going to march, 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 march. Now I make them go through my blow dryer. My blow dryer is an appliance that has a big R value. So it's got a lot of resistance. It's really going to slow my electrons down. And so they all kind of build up here in the blow dryer. And eventually they're going to pass through the blow dryer and they're going to be able to keep on going to something else. But while they're building up, it creates heat and it slows my electrons down. And so that concept of slowing electrons down and creating heat at the same time is the idea of power. We've already talked about power before, and the variable is P and the units are watts. You know that. But I just want you to think about that they generate heat. So that's a clue. My blow dryer gets hot. Your computer monitor, receiver, or CPU or stereo gets hot. A space heater, a light bulb, even light bulbs get hot. I plug in my coffee pot, it gets hot. I plug in my microwave, it gets hot. And so again, this idea of resistors collecting electrons is what generates our heat, which what brings the power in. And power also then, like we might remember it as work over time, but in this unit, work is the same thing as energy over time. So I'm going to cross this out. We're going to use power as energy over time. How much energy then do I get out per second? In my blow dryer, this would be, I get 1200 joules per second out of my blow dryer, which is why it's a 1200 watt blow dryer in this particular example. All right, so that's our equation for power. All right, the last thing that we have to talk about is Ohm's Law. Technically, Ohm's Law is this. V equals IR. So that is a very, very common equation. Like it's the most important equation in this whole unit of circuits. It's kind of like equivalent to F equals MA. It's everything. So voltage equals current times resistance. But there's also the concept of power that comes in then. And so when I bring power in, power equals current times voltage. Well, you can see that there's a V here and a V here and an I here and an I here. And so you can kind of substitute and you can mix and match. And honestly, you can mix and match so many times that you can come up with all of these equations over here. And that's really the power of Ohm's Law. Ohm's Law shows that this idea of V equals IR and P equals IV can work together, that you can solve a lot of problems just from these two simple equations. We use these equations so much. I named them PIV, P-I-V, PIV, and VIR, PIV and VIR, PIV and VIR. And next week, when we start to get together to do our circuit charts, which is the hard part of this unit, we will be doing VIR and PIV all the time, and that's what I'm going to refer to them as. So it might be helpful to kind of learn them that way. All right, so in summary, I want to do a problem with you here in a moment, but on the next page, the hard part about this lesson that we're doing is we have a whole bunch of new words and variables. So let's buzz through them real quick. So charge, we are now going to have electrons that are marching around our circuit. But these are still charges. And so the variable for charge is a Q, and we measure that in coulombs. So we'll write in coulombs, which is a C. We need an energy source for our circuit. That's going to be our battery. It's called voltage or potential difference. And that's going to be V. And the unit is going to be volts, which is also a V. Then my electrons are going to march kind of fast. And when they march fast, that's current. And current is named after Mr. Ampere. So it's amperes, or we'll use capital A, and it's okay to say amps. The resistance resists the flow of electrons and slows them down, and it's named after Mr. Ohm. So ohms, not an O, but Greek O. And then power, and that is named after Mr. Watt. So we call them watts with a W. So sometimes when you're doing problems, you can use the units that's attached to the number to help you figure out what variables that we're talking about. All right, equations that we're going to be using. This whole topic of circuits was, I'll say, invented by Mr. Ohm. So Ohm's law gets king up here, but how fast the electrons march could be coulombs per second. The resistivity in a wire, we have pla. We have our power if we need it. And we also can write power in terms of energy over time. So we have two different equations for power. I will tell you that this one is way more popular than the bottom one. And these are our main equations. All right, the homework assignment that goes along with this lesson is a WebAssign. And so our example here is we're going to do number 3 on the WebAssign. So I'll do it very quickly. All right, it says a 2,000 watt heater is constructed to operate as 220 volts. So I'm going to use my units as a clue. So that's watts. I know that means power. So 2,000 watts. And volts, so the voltage is 220 volts. This could be like a space heater. What will be the current in the heater? Casual language, how fast are the electrons marching through the heater? What will be the current? I equals question mark. So you can see here for letter A, P equals IV will probably be a good equation here. And it says 9.09 amps. Letter B, what is the resistance? R equals question mark of the heating coil. Well, I'm going to use V equals IR to solve for the resistance. Letter C, how much thermal energy is generated in 1 hour? So how much energy am I going to generate in an hour? So I'm going to use power equals energy over time. So my power is 2,000. 1, 2, 3. How much energy? And my time has to be in seconds. So that's going to be 3,600 seconds. And then when I solve for my energy, it'll turn out to be in joules. Okay, one more time. The homework is a WebAssign. And so if you can log into that, I think I have the WebAssign due on Tuesday or Wednesday night so that we can go, I think it's Wednesday, so that we can look at the second half of the unit, the second half of the week. Okay, hopefully that helps you.